Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to imagine, just for a second, that you are standing on this really high balcony.
Yeah, okay.
And you're looking down through a tremendously thick, slightly distorted telescope lens at a massive crowd of people in a city square.
Like a really heavy glass that warps the edges a bit.
Exactly. And because of the distortion, you can't see individual faces at all. But you can map out the fluid dynamics of the crowd.
Right, you can see how the energy transfers when people bump into each other.
Yeah. You watch how they move, how these ripples of movement cascade through the plaza, and they form these very distinct, mathematically predictable patterns.
You can basically write the rules of their movement.
You do. Over decades, you meticulously document these patterns. You write down the definitive laws of physics for how this specific group of people behaves based on, well, everything your lens allows you to see.
Which is a lot of rigorous work.
It's your life's work. But then a technological revolution happens. Someone hands you a brand new lens, one with a resolution that cuts right through all that atmospheric distortion. You look back down at that exact same city square, and a sudden, cold realization washes over you.
They're not the same people.
They are not the same people. The people causing those massive ripples, the ones driving the fundamental movement of the entire crowd. They aren't the group you spent your entire life studying.
It's an entirely different group.
An entirely different group of imposters wearing nearly flawless disguises has infiltrated the square, and they are secretly pulling the strings right in plain sight.
I mean, that forces a complete collapse of your foundational assumptions right there.
Completely.
You realize that what you thought was a rigorous understanding of the crowd's behavior was actually just a really rigorous understanding of the disguise.
And that structural collapse of our assumptions is exactly what we are plunging into today.
It's a massive topic.
We are looking at the ghostly, nearly invisible universe of subatomic particles that are swarming through your body, through the walls of the room you're in, right this very second. We are talking about the neutrino.
Right, the classic ghost particle.
But more fundamentally, we're examining a massive, almost incomprehensible cosmic identity theft. The goal of our conversation today is to explore this crazy tension between the absolute vastness of the cosmos and the tiny microscopic confines of the particle physics laboratory.
It really is the ultimate collision of macro and microphysics.
Because things aren't lining up.
No, they absolutely are not. The universe we observe through our most powerful telescopes is outright refusing to align with the physics we measure in our most precise underground detectors.
And the core of this tension comes from this incredibly provocative framework put forward by researcher Bhupal Dev and his colleagues at Washington University in St. Louis.
Published recently in Physical Review Letters, yeah.
Right, in April 2026. The physics community has been quietly wrestling with this glaring contradiction for years.
It's been the elephant in the room.
The problem is that what scientists confidently thought were strongly interacting neutrinos, shaping the earliest moments of the universe, might not be neutrinos at all.
Which is a terrifying thought for particle physicists.
Dev proposes they are a completely unconfirmed, highly elusive force known as dark radiation.
Because, when you are dealing with the absolute foundational building blocks of reality...
The stuff that makes everything.
Exactly. The particles that dictate how energy and matter coalesce into galaxies, into stars, and eventually into us, you expect consistency.
You demand it.
Right. But when the laboratory data definitively states a particle behaves one way and the cosmological data definitively shows it behaving another way...
You don't just have a rounding error.
No, you have a full-blown crisis in modern physics.
So, okay, to understand the crisis, we have to understand the victim of this cosmic identity theft. The standard garden variety neutrino.
The original suspect.
We call him ghostly, which, sounds very poetic. But in physics, that implies a very specific lack of interaction.
Yes, very specific.
What are the actual mechanics of a particle that essentially ignores the physical world?
Well, to grasp just how detached neutrinos are from our everyday reality, you really have to look at the forces they simply ignore.
Okay.
In the standard model of particle physics, which is our ultimate battle-tested rulebook for the quantum world, particles interact via 4 fundamental forces.
Gravity, electromagnetism, and the strong and weak nuclear forces.
Exactly. Now, neutrinos are electrically neutral.
Meaning they have no charge.
Right, meaning they don't feel the electromagnetic force at all. Think about it. An electron bounces off other electrons because their negative charges repel each other.
Like magnets pushing apart.
Yeah, and that electromagnetic repulsion is literally why you don't fall through your chair right now.
Because the electrons in my pants are pushing against the electrons in the chair.
Precisely. Neutrinos don't have that. They carry no charge, so they just breeze right past. Furthermore, they don't feel the strong nuclear force either.
And the strong force is the one that glues protons and neutrons together inside an atom's nucleus, right?
Right, it's the cosmic glue. But neutrinos are immune to it.
So they pass right through the electromagnetic fields of atoms, and they completely ignore the dense nuclei.
Like they aren't even there.
What force actually binds them to the universe at all, then?
They only interact through gravity, which is incredibly, almost unfathomably weak on a quantum scale.
Right.
And the weak nuclear force. Now, the weak force is responsible for radioactive decay, and as the name implies, it has an incredibly short range.
How short are we talking?
Well, for a neutrino to actually interact with a proton or a neutron via the weak force, it essentially has to score a direct head-on hit with the nucleus.
Like a microscopic bullseye.
Exactly. And because atoms are overwhelmingly composed of empty space, the probability of that direct hit, what physicists call the interaction cross-section, is vanishingly small.
I've heard this crazy statistic that to guarantee a neutrino from the sun would hit a single atom, you would need to build a wall of solid lead that stretches from the Earth all the way to Alpha Centauri.
4 light years of solid lead.
That is insane.
It really is. That is the barrier required to stop a particle that is currently passing through your thumbnail by the tens of billions every single second.
Tens of billions. And we don't feel a thing.
Nothing. When Wolfgang Pauli first mathematically proposed the existence of the neutrino back in 1930, just to explain some missing energy in radioactive decay, he was actually upset about it.
Really?
Yeah, he famously lamented, "I have done a terrible thing. I have postulated a particle that cannot be detected."
He thought he made up a ghost that could never be caught.
Exactly. And it took decades before Clyde Cowan and Frederick Rains finally caught a handful of them.
How did they manage that if they're so elusive?
They essentially cheated the odds. They set up a detector right next to a nuclear reactor, taking advantage of the sheer, overwhelming volume of particles being produced. If you have enough of them, eventually one hits the bullseye.
Okay, so that sets our baseline. We know how to catch them now, sort of. We build these massive observatories today.
Like Super Kamiokande in Japan.
Right, that gigantic underground cavern filled with, 50,000 tons of ultra-pure water?
Lined with thousands of golden photomultiplier tubes. It's beautiful.
Or IceCube, which uses a literal cubic kilometer of clear Antarctic ice.
Yeah, burying sensors deep in the glacier.
And we just wait. We wait for one of these trillions of neutrinos to occasionally hit an oxygen nucleus and produce this microscopic flash of blue Cherenkov light.
And because of those massive, precise facilities, the laboratory constraints on these particles are ironclad.
We know them intimately now.
We do. We know they are antisocial loners. They don't interact with regular matter, and they certainly don't interact with each other in any meaningful way.
Right. The standard model dictates that their self-interaction is virtually zero.
They are essentially free streaming through the universe, untethered.
And here is where the massive contradiction hits. The cosmological data is telling a completely different story.
And a dramatically different story.
The telescopes were looking back at the early universe, specifically at how the cosmic web of galaxies formed and how ancient radiation is distributed, and they are seeing the fingerprints of a heavily interacting particle.
Something that is bumping into things.
So, okay, let's unpack this. I have to challenge this contradiction directly.
Before.
If our underground water tanks and Antarctic ice sensors are these highly controlled, incredibly precise, isolated environments,
Which they are.
and outer space is this inherently messy, chaotic soup of variables, why on earth would we trust the telescope over the detector?
It's a fair question.
Why not just assume the astronomers are misinterpreting their messy data and the standard model is totally fine?
It's a vital skepticism. You always scrutinize the messier data set first. That's just good science.
Right.
But the cosmological evidence isn't just a single blurry photograph. It is an incredibly robust, interlocking web of independent measurements.
So it's not just one telescope getting a weird reading.
Exactly. When cosmologists look at the distribution of matter in the universe, they aren't just taking pictures. They are measuring the thermodynamic history of reality itself.
Okay, thermodynamic history. How do neutrinos play into that?
Well, neutrinos, despite being nearly massless, exist in such staggering quantities that they actually govern a significant portion of the universe's total energy density.
Because even if a particle weighs next to nothing, if you pack a trillion of them into a cubic parsec, that collective mass exerts real gravity.
Precisely. Now, in the early, incredibly dense, hot universe, particles were packed so tightly that even weak interactions happened constantly.
Everything was essentially touching everything else.
Right. The universe was an opaque, fluid-like plasma. But as the universe expanded and cooled, particles decoupled from each other. They stopped interacting and started flying free.
Like the crowds in the plaza suddenly spreading out into an empty field.
Great analogy. According to the Standard Model, neutrinos should have decoupled very early on and started free streaming.
Untethered, like we said.
And free-streaming particles smooth out the universe. Because they move at nearly the speed of light and don't clump together, they tend to wash away small gravitational fluctuations.
They act like an iron smoothing out the wrinkles in a fabric.
Exactly. They smooth out the cosmic web. But the telescopes are looking at the wrinkles, and the wrinkles are surprisingly deep.
Deeper than they should be if standard neutrinos were doing the ironing.
The data shows that the early universe behaved as if the neutrinos were not free streaming. It shows fluid-like dynamics.
Which implies
These particles were bumping into each other, exchanging energy, and creating localized pressure well past the point when the Standard Model says they should have been solitary ghosts.
So the math from the sky requires strong self-interaction.
Yes.
And the math from the lab forbids it.
Absolutely forbids it. And both datasets have been rigorously peer-reviewed, error-checked, and replicated.
That is the impenetrable wall.
We are stuck.
Because if it's the exact same fundamental particle, it cannot follow two completely different sets of physical laws, depending on whether we look at it through a microscope or a telescope.
That violates the very premise of universal physics.
Which leads us directly to Dev's paper. His keen solution to this paradox is just brilliantly subversive.
It really is an out-of-the-box approach.
They argue that the reason the ghost appears to be breaking the rules in outer space is because we aren't looking at the ghost at all.
We are looking at an imposter.
The cosmological signals we've spent decades interpreting as strongly interacting neutrinos are, under this framework, an entirely different, previously unknown form of energy.
Dark radiation.
But the obvious question is, how did an imposter fool some of the most advanced cosmological models ever created?
It sounds impossible, right?
Yeah. I mean, if we were looking at the universe and mapping out its thermodynamic history, how do we confuse a neutrino with something entirely different?
The confusion actually stems from the inherent limitations of our cosmic sensors.
Okay, what do you mean?
When we observe the early universe, we do not have a tool that acts as a microscopic particle name tag reader.
We can't just zoom in and see the label?
Right. We cannot look at a microscopic speck of ancient light and definitively say, an electron neutrino is here.
So what are we actually measuring then?
Instead, our observations primarily measure a parameter called NF. That stands for the effective number of relativistic species.
Okay, let's break down NF. Relativistic species basically means particles moving at or near the speed of light, right? Fast-moving energy.
Correct. The early universe's expansion was governed by the total energy density of everything in it.
Everything altogether.
Yeah. And NF is simply a measure of how much of that total energy was carried by fast-moving lightweight particles that do not interact with light.
Okay, so fast, light, and invisible.
Exactly. And in the Standard Model, the only particles that fit that exact description are the three flavors of neutrinos: electron, muon, and tau neutrinos.
I see where this is going.
Therefore, cosmologists naturally assume that whatever fast-moving, non-luminous energy they detect is entirely composed of neutrinos.
It's an issue of default attribution.
Exactly. We see the footprint and just assume the shoe.
Here's where it gets really interesting. Imagine a highway speed camera setup that measures kinetic energy.
Okay, I like this.
The camera looks through a thick fog, which is our billions of years of cosmic expansion.
Right.
It triggers only when something passes by at over 150 miles per hour, and it registers the exact speed and way of the object. But because of the fog, the visual is completely washed out.
You just get a blurry shape.
Right. If the city only manufactures one type of high-speed motorcycle, every time the camera registers a blur at 150, the local police logically assume that was one of our motorcycles.
The speed camera analogy gets right to the heart of the observational blind spot.
Because what if it isn't a motorcycle?
Dev and his team are arguing that there is a completely different vehicle on the highway. A fast-moving sports car that triggers the exact same kinetic energy sensors, travels at the exact same speed, but is structurally distinct.
And that sports car is dark radiation.
Exactly.
Now, the term dark radiation sounds deeply science fiction, but in physics, dark just implies an absence of electromagnetic interaction, doesn't it?
Right, it just means it doesn't emit, reflect, or absorb light.
Like how dark matter holds galaxies together through gravity but is otherwise invisible. Or dark energy pushes the universe apart. What sets dark radiation apart from those two?
Well, while dark matter is cold and slow-moving, clumping together to form the gravitational scaffolding of galaxies.
The heavy stuff.
Right. Dark radiation is hot and relativistic. It zips through the universe near the speed of light, carrying energy and momentum, but remaining completely isolated from the electromagnetic spectrum.
So it behaves kinematically just like a neutrino.
Identically. It's the sports car hitting the same speed on the sensor.
But if it behaves just like a neutrino, how does Dev's team suggest it got onto the highway in the first place?
Ah, the origin story.
Yeah. I mean, if it didn't exist in the standard model, did it just spontaneously generate to fix our broken equations? Because that feels a little too easy.
The origin mechanism is where the paper takes a massive philosophical leap regarding how we actually view fundamental reality.
Okay.
The dark radiation did not pop into existence independently out of nowhere. Dev proposes that in the extreme environment of the very early universe, a fraction of the actual standard neutrinos converted into dark radiation.
Wait, they converted?
Yes.
The particles changed their fundamental identity.
They did.
But we're taught in introductory chemistry and physics that particles are static building blocks, right? An electron is always an electron. A proton is a proton.
That's a classical view, yes.
But quantum mechanics suggests particles are actually just localized vibrations in an underlying field. So how does a neutrino suddenly decide to become dark radiation? What are the mechanics of that conversion?
To understand the mechanism, we have to look at phenomena we already know exist, specifically neutrino oscillation.
Okay, like the solar neutrino problem from a few decades ago.
Exactly that. Back then, we calculated exactly how many electron neutrinos the sun's nuclear fusion should produce.
Because we understand fusion really well.
Right. But our detectors on Earth were only catching about a third of the expected neutrinos. It genuinely seemed like the sun's energy output was fundamentally broken.
Which is terrifying.
But eventually, physicists realized the neutrinos were actually changing flavors. They were morphing from electron to muon to tau neutrinos as they traveled through space.
And our detectors were only tuned to catch the electron flavor.
Exactly. This happens because the flavor states of a neutrino do not perfectly align with their mass states.
That sounds complicated.
Think of it this way. As they travel through a vacuum, the quantum mechanical waves describing their probability interfere with each other. This causes the particle to periodically oscillate its identity.
So identity fluidity is already a baked-in feature of the neutrino. It's already something they do.
Yes. Dev is just taking that established oscillation and pushing it into a completely new, undiscovered physical sector.
Okay, so how does the push happen?
Dev hypothesizes a coupling between standard neutrinos and a new, incredibly light scalar field, or gauge boson.
A new piece of quantum machinery.
Exactly. In the intensely hot, dense thermal bath of the early universe, the ambient temperature and energy were high enough to trigger a massive phase transition.
So it's about the environment being extreme enough.
Right. Standard neutrinos, constantly interacting with this dense environment, were forced to undergo a massive shift, converting their state entirely into the dark radiation sector.
So going back to our highway, the motorcycle drove into a tunnel, which is the incredibly dense thermal bath of the early universe.
I like this.
And due to the extreme pressure and temperature inside that tunnel, the parts were essentially rearranged, and it drove out as a sports car.
A perfect analogy.
The speed camera way down the highway only catches the blur, so it assumes it's still looking at a motorcycle.
And here is the crucial, elegant twist that completely solves the contradiction we started with.
Let's hear it.
Unlike standard neutrinos, which are forbidden by the standard model from strongly interacting with each other.
Because they're antisocial.
Right. This newly formed dark radiation is allowed to self-interact. It exists outside the standard model constraints.
Ooh.
So when our telescopes look deep into the cosmos and see the fluid-like behavior, those deep wrinkles in the early universe suggesting particles were bumping into each other.
Sharing energy, acting like a fluid.
Yes. They aren't seeing rule-breaking standard neutrinos. They're seeing the dark radiation behaving exactly as it should.
Which totally protects the laboratory data.
Exactly.
The deep underground tanks on Earth are confirming that standard neutrinos are antisocial loners. That remains an absolute truth.
Unchanged.
And the telescopes in space are confirming that something was highly social and interactive in the early universe. That also remains an absolute truth.
The contradiction just vanishes.
Because the laboratory is studying the original particle and the telescope is looking at the aftermath of the imposter.
It is a mathematically beautiful resolution.
It really is.
However, in cosmology, introducing a monumental phase transition where fundamental particles rewrite their identities, it requires absolute precision.
Why is that?
Because if you dump a massive amount of new, strongly interacting energy into the early universe, you run the risk of completely destroying every other well-established model of cosmic evolution we have.
You can't just throw a wrench into the machine without breaking gears.
Right. To avoid burning the house down, this conversion had to happen within an incredibly specific, very narrow window of time.
It's the ultimate stealth operation. The imposter has to slip into the crowd when nobody is looking.
Precisely.
So when exactly was this blind spot? Let's walk through the timeline of the early universe to figure out exactly when this crime took place.
Well, the researchers pinpointed the temporal gap perfectly. The transformation of standard neutrinos into dark radiation had to happen after the epoch of Big Bang nucleosynthesis, but before the formation of the cosmic microwave background.
Okay, we need to pull those two massive eras apart to understand why they act as boundaries.
Yeah.
Let's start with Big Bang nucleosynthesis, often just abbreviated as BBN.
Right.
What are the physics defining this specific era?
Big Bang nucleosynthesis is the era spanning roughly from 10 seconds to 20 minutes after the initial expansion of the universe.
Just the first 20 minutes.
Yes. During this window, the universe was an unimaginably hot, dense soup of isolated protons and neutrons.
No atoms yet.
No, the temperature was so extreme that atomic nuclei could not hold together. They would instantly be blasted apart by high-energy photons. It was too violent.
So it's just raw ingredients flying around.
But as the universe expanded, it cooled. Right around the 1-minute mark, the temperature dropped just enough to about 1 billion degrees Kelvin.
Still pretty warm.
Just a bit. But cool enough to allow the strong nuclear force to finally overcome the ambient heat. Protons and neutrons began to successfully smash together and stick.
And that's fusion.
Yes, fusing to create the very first lightest elements in the cosmos, primarily helium-4, along with trace amounts of deuterium, lithium, and beryllium.
And what about the heavier stuff?
Everything heavier than that. The carbon in your cells, the iron in your blood, was forged billions of years later inside the collapsing cores of dying stars.
Okay, so BBN is the cosmic forge. It's the factory where the absolute foundational raw materials of reality were minted.
That's a great way to put it.
But why is it the starting line for our imposter's window?
Yeah.
If dark radiation converted during DBN, what would be the catastrophic result?
Well, the elemental recipe forged during BBN is exquisitely sensitive to the expansion rate of the universe at that exact moment.
Because the expansion rate controls the temperature.
Exactly. The expansion rate dictates the freeze-out temperature of the weak nuclear force, which in turn locked in the exact ratio of protons to neutrons.
What was that ratio?
For every 1 neutron, there were roughly 7 protons. That highly specific ratio is why the universe today is composed of about 75% hydrogen and 25% helium by mass.
And we know that for a fact.
We do. We measure that 25% helium abundance in the oldest, most pristine gas clouds in the universe, and it perfectly matches our standard model predictions.
Okay, I see the trap.
It's a tight constraint.
If the dark radiation conversion happened during the first 20 minutes, the massive shift in particle physics would have altered the thermal dynamics.
It would have dumped too much interacting energy.
Right. It would have changed the energy density, which would have accelerated or decelerated the expansion rate during the forge. The proton-to-neutron ratio would have shifted.
And the universe would have ended up with, say, 30% helium, or maybe just 15% helium.
But because it's exactly 25?
Right. The pristine primordial gas clouds act as a fossil record of those first 20 minutes. Because the fossil record shows no disruption, we know definitively that standard non-interacting neutrinos were doing their job perfectly during BBN.
The imposter hadn't put on the disguise yet.
Exactly.
So the forge shuts down around the 20-minute mark, the elements are locked in. That naturally opens the window for the dark radiation conversion.
Yes, the gap begins.
What closes the window? Why did the transformation have to finish before the cosmic microwave background formed?
For that, we have to move forward in time to roughly 380,000 years after the Big Bang.
That's a big jump.
It is, and for that entire intervening period, the universe was a violently glowing, completely opaque plasma of atomic nuclei, free-floating electrons, and photons of light.
It was essentially the interior of a star, but stretched across the entire cosmos.
Exactly. And because electrons carry a negative charge, they fiercely interacted with the photons of light through a process called Thomson scattering.
What does that actually look like?
Imagine a photon trying to travel in a straight line, but it instantly ricochets off a free electron, bouncing wildly inside the plasma, over and over.
So the light was essentially trapped.
Completely trapped. The universe was filled with light, but if you could somehow stand there, you wouldn't be able to see anything but a glowing, blinding fog.
Okay, so what changes at the 380,000-year mark?
Well, as the expansion continued, the ambient temperature relentlessly dropped. Right at that mark, the temperature dipped below 3,000 Kelvin.
Which is the magic number.
It is. Suddenly, the chaotic, fast-moving free electrons lost enough kinetic energy that they were finally captured by the electromagnetic pull of the hydrogen and helium nuclei.
They snapped into orbit.
Yes. The first true electrically neutral atoms formed. This event is called recombination.
And because the electrons were finally locked down into orbits, they were cleared from the highway.
The photons of light stopped ricocheting. They suddenly had a clear, unimpeded path through space. The fog instantly lifted, and the universe became transparent.
It's like turning on the lights in the universe.
That massive, simultaneous burst of free light has been traveling unhindered across the cosmos for 13.8 billion years.
Which is what we call the CMB.
Right. The expansion of the universe has stretched the wavelengths of that light, cooling it down into the microwave spectrum, the cosmic microwave background.
It's the literal afterglow of creation, a pervasive hum of radiation sitting at a frosty 2.7 degrees above absolute zero.
And it is the ultimate baby picture of the universe.
Now, when we look at it with satellites like WMAP or Planck, we don't just see a smooth, uniform glow, do we?
No, we see microscopic temperature fluctuations, tiny, incredibly faint hot and cold spots scattered all across the sky.
And why are those spots so important?
Those temperature fluctuations are arguably the most vital data points in all of cosmology. They represent the primordial density ripples where matter was just beginning to clump together under the force of gravity.
Oh, so those are the seeds of galaxies.
Exactly. Those tiny microscopic clumps eventually grew over billions of years into the massive superclusters of galaxies we see today.
And what created the ripples in the first place?
The distribution of those hot and cold spots is dictated by acoustic waves, literal sound waves that were bouncing through the plasma before recombination froze everything in place. We call them baryonic acoustic oscillations.
Okay, this connects perfectly back to Dev's timing constraint.
You see it?
If the neutrinos converted into dark radiation after the CMB formed, the sudden injection of a new, interacting energy force would have disrupted the gravitational evolution of those tiny density ripples.
Exactly. We would look at the distribution of galaxies today, and they wouldn't match the baby picture from the CMB.
So the conversion had to happen within the opaque plasma before the lights turned on.
By transforming in the dark gap between 20 minutes and 380,000 years, the dark radiation was able to fundamentally alter the acoustic waves bouncing around the plasma.
Baking its disruptive noise into the CMB structure.
Right, but doing so in a way that perfectly mimics standard cosmological models. It effectively erased its tracks before the grand architecture of the modern universe was ever built.
That is just incredible. The implications of uncovering an invisible force that quietly reshapes the acoustic waves of the early universe are staggering.
It changes everything.
Because if we fundamentally misunderstood the primary actors on that early stage, the ripple effects for modern astrophysics must be immense.
They are. And Dev's paper isn't just trying to solve a niche particle physics contradiction here.
No, he's aiming much higher.
He's suggesting this exact dark radiation mechanism could actually resolve the single most destructive crisis in modern cosmology.
The Hubble tension.
The Hubble tension. It is the dark cloud hanging over the entire field of astrophysics right now.
To put it plainly, our fundamental measuring tape for reality is broken.
That's the best way to describe it.
We have known since Edwin Hubble's observations in the 1920s that the universe is not static. It is expanding outward in all directions.
And the rate of that expansion is known as the Hubble constant.
Measuring that exact constant is arguably the most important task in cosmology, right? Because it dictates the age, size, and ultimate fate of the universe.
Yes. If you don't know the expansion rate, you don't know how old the universe is or where it's going.
So if the measuring tape is broken, it implies we have two different methods of measuring the exact same room, and they are returning violently different square footage.
Violently different.
Let's dig into the physics of how we actually measure the expansion of the universe. What is the first method?
The first method is looking at the early universe, specifically utilizing the cosmic microwave background we just discussed.
The baby picture.
Right. Cosmologists analyze those microscopic hot and cold spots in the CMB to measure the maximum distance a sound wave could have traveled through the primordial plasma before recombination froze everything in place.
The baryonic acoustic oscillations.
Yes. That maximum distance is called the sound horizon, and it serves as an incredibly precise standard ruler for cosmologists.
So they figure out how big that ruler was in the early universe.
By calculating the physical size of that standard ruler back then, and then observing its angular size in the sky today, we can use the standard model of cosmology, which is called lambda CDM.
To mathematically project it forward.
Exactly. To extrapolate exactly how fast the universe must be expanding right now to make the math work out.
So that CMB method is highly theoretical. It relies on the baby picture, builds a mathematical model of how the baby should age, and predicts its adult height.
Right, it's perfectly stated.
And what is the specific number it predicts?
The CMB data, which was captured flawlessly by the Planck satellite, predicts a modern expansion rate of roughly 67.4 kilometers per second per megaparsec.
Okay, 67.4. That's the baseline expectation. Now, what is the second method? Because if the first method predicts the adult height, the second method must be, pulling out a tape measure and looking at the adult in real time.
The second method relies on direct, local, modern-day observation. It uses something called the cosmic distance ladder.
How does that ladder work?
Astronomers look at nearby galaxies and find specific pulsating stars called Cepheid variables.
Why those stars in particular?
Thanks to the groundbreaking work of Henrietta Swan Leavitt over a century ago, we know that the rate at which a Cepheid pulses is directly tied to its true intrinsic brightness.
Oh, so if you know how fast it blinks, you know exactly how much light it's actually pumping out.
Exactly. By comparing how bright the star actually is to how dim it appears from Earth, we can calculate its exact distance.
Just like estimating how far away a car is on a dark road by looking at how dim its headlights are.
That's the exact principle. And once we have the distance to the nearby galaxies using Cepheids, we can use them to calibrate even brighter markers, like Type Ia supernovae, to measure galaxies much, much further out.
And that builds the ladder.
That's the distance ladder. We measure the distance to these galaxies, and then we measure their redshift.
Redshift being how much the light stretching from those galaxies has shifted into the red end of the spectrum due to the expansion of space itself.
Right. By plotting the distance against the redshift, we get a direct, empirical measurement of the Hubble constant today. Teams like the SH0ES project, utilizing the Hubble and James Webb Space Telescopes, have refined this measurement to an agonizing degree of precision.
And their real-time measurement returns a completely different number.
They calculate an expansion rate of roughly 73.0 kilometers per second per megaparsec.
67.4 from the early universe prediction, and 73.0 from the modern local observation.
That's a massive gap.
In the past, scientists just assumed this discrepancy was due to sloppy instruments, didn't they? They assumed that as our telescopes got better, the error bars would shrink, and the two numbers would slowly meet in the middle, maybe settling around 70.
That was the hope for a long time. But the exact opposite happened.
The gap held.
As the instruments became flawlessly precise, the error bars shrank, but the numbers refused to move. The 67.4 stayed at 67.4. The 73.0 stayed at 73.0.
So it's not instrument error.
No. The gap between them is now statistically significant to 5 sigma.
Which in physics means?
It means there is less than a 1 in a million chance that this disagreement is a random fluke. It is a severe structural failure of our standard model.
I want to build a visual analogy for this to really cement it.
Let's do it.
Imagine trying to calculate the speed at which a massive hot air balloon is inflating.
Okay.
The direct local observation method, the supernovae and the distance ladder, is like taking a Sharpie, drawing 2 dots on the rubber of the balloon, and using a high-precision stopwatch to measure exactly how fast the rubber is stretching those dots apart.
Right. It is an undeniable physical observation of the current state.
Exactly. The early universe method, the CMB, is entirely different. Instead of looking at the rubber, you're placing a microphone inside the balloon when it was much smaller, listening to the acoustic resonance, the pitch of the sound waves bouncing around the interior.
The baryonic acoustic oscillations.
Right. You use complex acoustic physics to calculate the exact volume of the balloon based on that pitch, and then you mathematically project how fast the rubber should be stretching today based on the internal pressure.
That is an excellent framework. The tension exists because the acoustic math says the balloon should be inflating slowly, but
our eyes watching the rubber say it is inflating quickly.
Exactly. For a decade, physicists have been fiercely debating whether our microphones were faulty or our stopwatches were broken.
But neither is broken.
No. Dev's introduction of dark radiation suggests that our instruments are totally fine. The problem is that we fundamentally misunderstood the physical properties of the air inside the balloon.
How does replacing standard neutrinos with dark radiation fix the physical properties of the early universe and actually bridge that massive mathematical gap?
It all comes down to energy density and the sound horizon we talked about earlier.
The standard ruler.
Yes. Remember, the early universe expansion rate is driven by the total energy density within it. If standard neutrinos underwent a massive conversion into dark radiation in that gap before the CMB formed, the complex mechanics of that conversion.
Specifically going from a heavier, non-interacting state to a lighter, rapidly interacting state.
Right. That specific conversion would result in a subtle but significant net increase in the effective relativistic energy density.
So more fast-moving energy gets injected into the primordial plasma.
Exactly. And more energy density means stronger gravitational and pressure dynamics.
Which forces the early universe to expand faster than the standard model originally predicted.
Now, follow the logic. If the early universe was expanding faster, the plasma was cooling faster.
Okay, so it hits the 3,000 Kelvin mark sooner.
Yes. That means the 380,000-year mark, the moment of recombination when the CMB formed and the sound waves froze, actually happened sooner in physical time.
Oh, wow. Which means the sound waves had less time to travel before everything froze.
That is the crucial key. If the sound waves had less time to travel, the maximum distance they covered, our standard ruler, the sound horizon is physically shorter than we previously calculated.
The ruler shrank.
It shrank. So when cosmologists run the mathematical extrapolation, they measure the angular size of the spots in the CMB, and they divide it by the length of the standard ruler.
Basic geometry.
Right. If the underlying ruler is suddenly shorter because of the dark radiation, the math automatically forces the extrapolated modern expansion rate to jump up.
It pushes the 67.4 up to perfectly match the 73.0.
It does. The acoustic calculation of the balloon's pitch finally aligns with the stopwatch measuring the stretching rubber. The tension is broken.
That is incredibly elegant.
It bridges the gap beautifully without requiring us to discard the absolute baseline laws of quantum mechanics.
It just highlights a blind spot.
Dev's framework highlights a massive degeneracy in cosmology, an overlapping, essentially indistinguishable identity between free-streaming standard neutrinos and strongly interacting dark radiation.
So by just shifting the slider toward dark radiation in the early universe, you solve the macro and microneutrino interaction mismatch.
And as an incredible secondary effect, you provide a robust theoretical pathway to resolving the Hubble tension.
Okay, I have to play the skeptic again here.
Always.
Because the history of physics is absolutely littered with mathematical band-aids that turned out to be total illusions.
True.
It feels almost uncomfortably convenient. Our acoustic equations aren't balancing, so we invent a completely invisible, highly specific dark radiation, dictate that it appears perfectly in an unobservable time window, and magically, the math works out.
It sounds a bit rigged.
Yeah, a critic might argue that this is the modern equivalent of epicycles. You know what? When ancient astronomers added completely arbitrary imaginary loops to planetary orbits just to preserve the flawed idea that the Earth was the center of the universe.
Right, trying to save a dying theory.
Exactly. Are we just adding theoretical loops to avoid admitting our fundamental models of gravity are completely wrong?
That level of skepticism is the absolute bedrock of good science. theoretical physics is highly susceptible to mathematical pareidolia.
Seeing patterns that aren't real.
Right, seeing patterns and solutions that aren't physically real just because the equations technically allow them. However, the distinction between an arbitrary epicycle and a robust physical theory lies in its origin and its interconnected predictive power.
Okay, explain that distinction for Gev's paper.
Dev isn't just inventing a parameter out of thin air to fix the Hubble tension. The conversion mechanism relies on extensions of the standard model that are already necessary to explain why standard neutrinos have any mass at all.
Oh, really?
Yes. Concepts like the seesaw mechanism or the introduction of Majoron models.
So the scaffolding for dark radiation already exists within the attempts to solve other established particle physics mysteries.
Precisely. A mathematical band-aid only covers one specific wound.
Right.
But when a single theoretically grounded mechanism, like a phase transition into a dark sector, organically resolves the neutrino interaction mismatch,
While simultaneously providing a thermodynamic solution to the Hubble tension.
and offering pathways to understand neutrino mass generation, that theoretical weight completely shifts the perspective.
It's solving too many problems at once to be a coincidence.
It begins to look less like an artificial epicycle and much more like a genuine glimpse at a deeper underlying symmetry in nature.
But theoretical weight, no matter how elegant or interconnected, remains firmly in the realm of philosophy until it intersects with observation.
Physics demands physical proof.
Exactly. If this dark radiation is deliberately invisible and intentionally erased its tracks by hiding behind the blinding fog of the cosmic microwave background, how do we ever move this from a brilliant mathematical hypothesis to a confirmed physical reality?
We have to hunt it down.
How do we hunt down a ghost that wears a disguise?
Well, Dev is exceptionally clear in the paper that this mechanism is highly testable. Dark radiation may be invisible to the electromagnetic spectrum, but it carries energy and momentum.
Which means it inevitably interacts with gravity.
It leaves a footprint. And the next decade of observational astronomy and terrestrial laboratory physics is perfectly aligned to trap this imposter.
We are closing the net.
We are approaching the problem from two diametrically opposed scales: the macro scale of the entire cosmos and the micro scale of quantum decay.
Let's start with the macro, the cosmic dragnet. The paper highlights an emerging observational frontier called 21-centimeter cosmology.
Yes.
The name alone sounds radically specific. What makes exactly 21 centimeters the key to unlocking the dark sector?
To understand 21-centimeter cosmology, we have to revisit the timeline of the universe immediately following the formation of the CMB.
So right after the lights turned on at 380,000 years.
Right. At that mark, the first neutral hydrogen atoms formed. Now, for the next several hundred million years, before gravity could pull enough material together to ignite the very first stars, the universe was engulfed in pitch blackness again.
So the lights turned on, the CMB blasted outward, and then it got dark.
Yes. It was a dark, expanding ocean of cold, neutral hydrogen gas. Astrophysicists refer to this massive unlit epoch as the cosmic dark ages.
If there is no starlight, no galaxies, and no fusion occurring, how do we observe an era of pure darkness?
The darkness is an illusion of the visual spectrum. Neutral hydrogen gas is not completely silent.
What is it doing?
A hydrogen atom consists of one proton and one electron. Both of these particles possess a quantum property called spin.
Okay.
Very rarely, the magnetic interaction between the proton and the electron causes the electron's spin to spontaneously flip its orientation from parallel to anti-parallel.
Just a tiny microscopic flip.
And when that microscopic spin flip occurs, the atom releases a tiny burst of energy in the form of a radio wave.
And let me guess the wavelength.
With a highly specific, immutable wavelength, exactly 21 centimeters.
So the entire ocean of darkness during those hundreds of millions of years was actually humming with this faint, pervasive radio frequency.
Yes. And because the universe has been expanding for 13 billion years since that signal was emitted, those 21-centimeter waves have been stretched into much lower frequencies by the time they reach Earth today.
Oh, we try to listen to it.
We are. Cosmologists are currently building massive radio telescope arrays, sprawling networks of thousands of antennas laid out across isolated, radio-quiet deserts in Australia and South Africa.
Like this square-kilometer array.
Exactly. They are attempting to map the faint, red-shifted hum of that ancient hydrogen gas.
That is an astonishing technical feat. But how does mapping a hydrogen hum from the Dark Ages catch our dark radiation imposter?
Because the intensity and the absorption profile of that 21-centimeter signal are exquisitely sensitive to the thermal history of the gas.
Meaning its temperature.
Yes, the gas temperature dictates the rate of those electron spin flips. If standard neutrinos populated the early universe, the gas cools at one specific, perfectly predictable rate.
But if dark radiation was present?
Altering the expansion rate and the fundamental energy density of the cosmos.
The hydrogen gas would have decoupled from the ambient thermal bath differently.
Exactly. The thermodynamic footprint of dark radiation would fundamentally shift the timing and the depth of the 21-centimeter absorption trough.
So we aren't looking to see the invisible dark radiation directly.
No, we are mapping the intricate thermal indentations it left in the primordial gas clouds.
It's literally like trying to prove an invisible ship passed through the ocean at night by meticulously analyzing the specific shape, temperature, and frequency of the wake it left behind.
That is exactly the methodology. And 21-centimeter cosmology will be combined with large-scale structure surveys, too.
Like what?
Observatories like the Vera C. Rubin Observatory in Chile and the Dark Energy Spectroscopic Instrument, they are mapping the precise three-dimensional locations of tens of billions of galaxies.
Building a 3D map of the universe.
They are looking at the massive cosmic web to measure those baryonic acoustic oscillations, those ancient sound waves from the early universe that eventually froze into the permanent distribution of galaxies.
Oh, because dark radiation alters the pressure of the primordial plasma. It subtly shifts the clustering pattern of these galaxies across billions of light years.
You've got it. If standard neutrinos dictated the clustering, the web looks one way. If dark radiation dictated it, the galactic distances will show a very specific, mathematically measurable structural deviation.
So the macro scale uses telescopes the size of deserts and mountains to map the gravitational and thermal wake of the imposter.
That's the cosmic approach.
But what about the microscale? The paper states that terrestrial laboratory experiments are just as crucial in confirming this theory.
They are the other half of the pincers.
Which is profoundly ironic. The highly restrictive laboratory constraints are what created this paradox in the first place, and now we're relying on those exact same laboratories to save us.
It's the beauty of the scientific method.
How do quantum detectors hunt for dark radiation?
On the microscale, the hunt revolves around pushing the standard model to its absolute breaking point, specifically searching for anomalies in particle mass and oscillation. One major avenue is the hunt for the sterile neutrino.
Now, a standard neutrino is incredibly elusive because it only interacts via gravity and the weak nuclear force. Does sterile imply a particle that is even further detached from reality?
Exactly. A sterile neutrino is a hypothetical particle that does not even feel the weak nuclear force.
So it only feels gravity.
It only interacts with the rest of the universe purely through gravity. It is the ultimate quantum ghost.
Wow.
Certain particle physics models suggest that dark radiation could be fundamentally linked to or even composed of sterile neutrinos.
But how do you detect something that actively refuses to interact with your detector?
You have to look for disappearance.
Like the solar neutrino problem again, where we knew how many particles should be there and realized a third of them were missing.
Precisely. Experiments like the Short Baseline Neutrino program at Fermilab do exactly this. They shoot a highly concentrated, precisely counted beam of standard muon neutrinos toward a detector.
Okay, so they know exactly what's in the beam.
If, along that short journey, a tiny fraction of those standard neutrinos spontaneously oscillate into a sterile state or dark radiation, they will essentially vanish from the beam entirely.
The detector will register fewer standard neutrinos arriving than were initially fired.
Right. And proving the existence of a sterile neutrino state would provide the exact undeniable microscopic mechanism Dev requires for his massive early universe phase transition.
It proves that the identity of these particles can, in fact, vanish into an unobservable sector.
It provides the literal blueprint for the imposter's disguise.
And alongside the sterile neutrino hunt, the paper also mentions measuring the absolute mass of a standard neutrino.
Yes, the mass problem.
We know they have some microscopic mass because oscillation actually requires mass differences, right?
Yes, they can't oscillate if they are perfectly massless.
But we still don't know their exact weight.
Pinning down that absolute mass is the holy grail of terrestrial neutrino physics. The premier experiment attempting this right now is Katrin, located in Germany.
Tell me about Katrin.
It is an utterly massive, blimp-sized stainless steel spectrometer that measures the radioactive beta decay of tritium.
Tritium being a heavy isotope of hydrogen.
Right. When a tritium nucleus decays, it emits an electron and an electron antineutrino. Now, the total energy of that decay is always constant.
Energy is conserved.
Always. So if you measure the absolute maximum energy the emitted electron carries,
Whatever tiny fraction of energy is missing from the total must equal the mass of the invisible antineutrino that escaped?
that is the incredibly delicate balancing act Catron performs. They are weighing the missing energy.
That is genius.
Now, right now, the cosmological limits on the combined mass of all three neutrino flavors, which are derived from studying the CMB and the cosmic web under the assumption of standard non-interacting particles, sits at less than 0.12 electron volts.
Less than 0.12. That is an infinitesimally small number.
But the current terrestrial limit from Catron sits higher, around 0.8 electron volts.
This is where the trap closes on the imposter.
You see it?
If Catron, or a next-generation laboratory experiment, eventually pins down the absolute kinematic mass of the neutrino,
And that mass is definitively higher than the cosmological limit.
say 0.4 electron volts,
It shatters the cosmological assumption entirely.
it definitively proves that the highly restrictive mass limits derived from the telescopes are fundamentally incorrect.
And the only way the telescopic limits can be incorrect is if the CMB and the cosmic web were shaped by dark radiation, rather than the heavier standard neutrinos we measure in the lab.
It perfectly eliminates the prime suspect.
Yes.
If the laboratory proves standard neutrinos are too heavy to have caused the specific ripples we see in the early universe, then the universe had to be shaped by an imposter.
The pieces fit together flawlessly.
The macro observations from the radio deserts and the micro observations from the giant spectrometers are closing in on the exact same phenomenon from opposite ends of physical reality.
Dev's theoretical framework is profoundly powerful, precisely because it refuses to remain a pure thought experiment.
It makes predictions.
It makes highly specific, mathematically rigorous predictions about the thermal wake of hydrogen gas, the structural clustering of billions of galaxies, and the quantum disappearance of particles in a beam.
That's all testable.
Over the next decade, as these massive technological marvels, the square kilometer array, the Rubin Observatory, the upgraded terrestrial detectors, come fully online and cross-reference their data, the disguise will be stripped away.
We will know definitively if the imposter is real.
We will.
What an unbelievably disorienting yet elegant scientific journey. We began with a seemingly impossible contradiction.
The clash between the lab and the sky.
Right. The rigid, undeniable data from our terrestrial laboratories dictating that neutrinos are solitary, weakly interacting ghosts. Completely at odds with the sweeping telescopic data showing a universe molded by a highly interactive fluid-like particle.
A paradox that demanded a solution.
And then we unpacked Bhupal Dev's breathtakingly subversive proposal, the idea that the extreme thermal crucible of the early universe forced a massive quantum phase transition.
Converting a fraction of standard neutrinos into an entirely invisible, fast-moving imposter known as dark radiation.
We saw how this imposter managed to pull off the ultimate cosmic heist, slipping perfectly into the unobservable gap between the nuclear forge of Big Bang nucleosynthesis and the clearing fog of the cosmic microwave background.
Hiding its tracks in the dark.
And most remarkably, we explored how unmasking this imposter doesn't just resolve a niche interaction paradox, but mathematically bridges the gaping 5 sigma divide of the Hubble tension.
Fundamentally rewriting our understanding of the universe's expansion.
It really is a triumph of theoretical physics.
And the entire investigation serves as a profound testament to the necessity of relentless critical thinking, not just in theoretical physics, but in any arena where we rely on complex information.
That is so true.
We are perpetually surrounded by data. In this scenario, the initial data seemed irrefutable. Our cosmic sensors measured fast-moving energy. Our model said neutrinos were the only particles that fit the profile, and so we naturally assumed the case was closed.
We thought we knew exactly who was in the plaza.
But true scientific discovery demands that we look at the contradictions not as failures, but as doorways. It requires us to actively interrogate our most foundational assumptions.
To look for the blind spots.
To recognize the blind spots in our instruments, and to genuinely entertain the terrifying possibility that we have been fundamentally misinterpreting the actors on the stage.
The most profound truths about reality usually hide right behind the concepts we assume are completely settled.
The settled science is often just the disguise we haven't seen through yet.
It leaves you with a lingering, almost vertigo-inducing thought as you step back into your daily routine.
It really does.
If one of the most abundant foundational building blocks of the universe, a particle currently streaming through your cells by the trillions, a particle essential to the nuclear fusion that powers the sun,
If that could secretly rewrite its fundamental identity.
undergo a massive phase transition and masquerade as an entirely different form of invisible radiation, quietly dictating the geometric expansion of the cosmos completely undetected.
You have to wonder.
What else is wearing a disguise? What other ironclad, universally accepted laws of physical reality are merely temporary illusions, just waiting for the day we build a slightly sharper lens, a slightly more sensitive detector, and realize we've been staring at an imposter the entire time?